Hi folks, these are the recitation problems from Wednesday, March the 24th. I'm going to do both problems in this one video. So here we have a toy gun shooting a little plastic bullet down a tube with a spring. This compression distance, which I know I'm going to use, I'm going to call this delta x. Assuming that there is no friction as the ball moves down the barrel, is the total mechanical energy conserved? Yes, it is. Remember, mechanical energy is kinetic energy plus potential energy. Um, and potential energy just means energy associated with forces that are conservative. So in this problem, there are no non-conservative forces. So a non-conservative force, one like kinetic friction, is one that transforms energy from kinetic energy to some other type that we cannot associate with a potential energy. Um, so here, that's true. There are no non-conservative forces. What are the initial potential energy and kinetic energy? Well, here, we'll do the kinetic energy first because that one is super easy. The initial kinetic energy is just 0 because it's not moving. The initial potential energy, well, that is the elastic potential energy, which is 1/2 k delta x squared. You can just remember that that's the formula for elastic potential energy. It comes from doing an integral. Comes from integrating the spring force kx dx, but you don't need to remember that. You don't need to do that integral. Just remember that the potential energy in a compressed spring is 1/2 kx squared. What are the final potential and kinetic energy? Well, at the end, the spring has released. So in the end, the final potential energy is 0 since the spring is no longer compressed. And the final kinetic energy is going to be 1/2 mv final squared. We don't know how much that is, but that's fine. With what speed does the ball leave the end of the barrel? Well, I know that since there are no non-conservative forces, I can write down the conservation of energy / work energy theorem like this. So I know that the initial kinetic energy plus the initial potential energy plus the work done by other forces, forces which correspond to non-conservative forces, which of course I don't have any of in this problem, equals the final kinetic plus the final potential energy. Again, some of these terms are 0. I know there's no initial kinetic energy. I know there's no final potential energy. So this just gives me 1/2 k delta x squared equals 1/2 mv final squared. This tells me that v final, let's see, the 1/2s are going to cancel. Zoop, zoop. Tells me that v final is going to be equal to delta x times the square root of k over m. In part E, though, now we have turned on another source of work. We have a non-conservative force, this frictional force, and now we need to think about the work that it does. So now I've got the same expression. I'm going to not write down well, yeah, I will. I'll start from the beginning. I'll cross out all the things that are 0 again. Plus potential energy initial. Plus, now here we do have the work done by friction equals the kinetic energy final plus the potential energy final. It's always the same form. Kinetic plus potential plus work done by other forces equals kinetic plus potential final. That's 0. That's 0. And the work done by friction, this is just the force of friction dotted with the displacement, which is going to be minus FF times, we'll use L for the displacement. So this figure up here, that's 30 centimeters, I was thinking it was at the top, that I'll call L. So this tells me that, again, the initial potential energy is 1/2 K delta x squared minus the force of friction times the length equals 1/2 mv final squared. So now, when we substitute this in, now we're going to get, in the end, that v final is, let's see, it's going to be the square root of a whole bunch of stuff. Going to multiply through by 2 here, so this is going to give me k delta x squared minus 2 times the force of friction times the length. Clean up our radical sign a little bit, make it the right length. There we go. I'm not going to put in the numbers for this problem because oh, I completely forgot the mass. Sorry. I'm going to erase this and do it right. I forgot to divide by the mass. It's close to midnight and I'm very tired. So again, in the numerator, I've got k delta x squared minus 2 times the force of friction times the length, all divided by the mass. So you'll see that the first term here matches what we got before. So that matches this first term when divided by the denominator. But then there's also the second piece, which makes sense because it's slowed down by friction. All right, on to problem 2. Consider the roller coaster ride as shown below with the heights indicated. The total mass of these things is 400 kilograms, and the velocity of the car at point A is 5 meters per second. Assume no energy is lost due to friction as it makes its way down the track. So we're calling this point y equals 0. What is the total energy of the roller car at point D? How do you know? There are no non-conservative forces here doing work. The only forces here are gravity and the normal force. And we already know that the normal force doesn't do any work because it's always pointed perpendicular to the motion. So we'll make a note here that the normal force does no work. So in that case, the total mechanical energy is conserved. So at point D, we're going to have lots of kinetic energy. At point A, we have lots of potential energy. And as we go from A to D, potential energy is being converted into kinetic energy. But since energy is conserved, right, since mechanical is conserved, the energy at D equals the energy at A, which is going to be potential plus kinetic, which is 1/2 m times the velocity at A squared plus mg times the height of A. So that's going to be equal to 1/2. The mass is 400 kilograms. I'll actually put in the numbers in this problem because there's something interesting to see here. The velocity at A is 5 meters per second, meters per second, all quantity squared. Notice we have kilograms meters squared per second squared, which is joules, plus the mass again, 400 kilograms, times g, which is 10 meters per second squared, times the height at A, which is 40 meters. So adding these together in my head, let's see, 400 times 25 is 10,000. Divided by 2 is 5,000 joules on the, no, ooh, no, 400 times 25, yep, that's 10,000 joules of kinetic energy. And over on the right, we've got, I'm just doing the math in my head, you all can do it in your calculators. I have 400 times 10 is 4,000 times 40 more is 160,000. So the total energy here is 165,000 joules. That seems like an enormous amount of energy, and it is, but remember, this is a roller coaster with a mass of 400 kilograms, 880 pounds for the Americans, that's moving down 40 meters. So this is indeed a giant pile of energy. Okay, on to part B. Determine the velocity at point C. That's 15 meters high. So I'm going to do again energy before equals energy after. So I've got 1/2 mva squared plus mg times the height of A equals 1/2 mvc squared, erase, equals darn it, my apologies, it's late, plus mgyc. So kinetic plus potential equals kinetic plus potential. There's no external force doing work because of this idea, so I don't need another work term. So all that's left now to do is to solve for v sub c. So v sub c, it's going to be the square root of now I notice that all the m's cancel, right? That's kind of neat. I get va squared plus 2 gya minus 2g, whoop, stylus messed up there, 2gyc. Drew a really big square root sign, didn't actually need one. And you all can put in the numbers. Notice these terms make sense. I'm going to be going faster at C if I start faster, if I start higher, but I'm going to be going slower at point C if point C is itself higher in the air. Part C finally says if a second car came and had the same velocity at point A but double the mass, how would the velocity at D compare to the velocity of the first car? The mass of the car doesn't matter, right? We canceled it a bit ago, right? It would be the same. Note that M canceled. So this is kind of a very simple, bare bones way to look at gravitational potential energy. I want to make one final note before I end the video here. Notice that in this equation, I could rearrange this equation as follows. I'm going to move all of the velocity terms on the left, and I'm going to move all of the gravity terms on the right. So what's that give me? So I'm going to do it the other way. I'm going to put all the velocities on the right, and I'm going to put all the gravities on the left. So I get, oh, wrong tool. What I'm about to do is I'm about to show how potential energy and the work energy theorem are really equivalent. So I get mgya minus mgyc equals 1 half mvc squared minus 1 half mva squared. Now, notice that this thing on the left, if I distribute the mg or undistribute the mg, as you may prefer, this is mg times ya minus yc, which is really just the work done by gravity, force times distance. And this over on the right, whoops, I am sorry, my um, writing program crashed. It keeps automatic backups. I am loading from backup. And here we are. Yes, here we are. I lost just a little bit of work. So I didn't lose any work at all. These backups are pretty good. Um, this is just the change in kinetic energy. So notice that the approach that we took here using potential energy, with a little algebra, I can show that it's equivalent to the approach that I took over here with the work energy theorem. I've often had students ask me, how do you know when to use potential energy and when to use the work energy theorem? You may use either because they're equivalent. Just for every force, either think about it as attached to a potential energy, which you can only do for gravity and springs, or think about it as a force that does work and calculate the work done by that force. Thank you all. I will upload some more videos later.